In this video, we will cover solving antiderivatives using the method of u-substitution. Here, we have a list of common antiderivatives. It is important to have these memorized as they will likely be present on the AP exam. You can also find this list on the laminated sheet handed out to us in class.
We use antidifferentiation to evaluate both definite and indefinite integrals. The family of all antiderivatives of a function f of x is the indefinite integral with respect to x. That is to say that the integral contains no bounds. So using the common antiderivatives we just learned, let's evaluate an indefinite integral. So we have the integral of 3x to the fourth minus 2x to the negative third plus secant squared x dx. So to evaluate this, you can break it up into the three parts you see here. To begin, we're going to use the power rule to solve 3x to the fourth. So it becomes 3x to the n plus 1, so that's going to be 5 over 5, minus 2 to the x to the negative 2 over negative 2, and then, as you saw on the previous slide, the antiderivative of secant squared x is tangent x. And remember, you need your constant of integration, so that's going to be plus c. So now let's simplify some things a little bit because these two negatives are going to cancel. So your final answer ends up being 3x to the fifth over 5 plus x to the negative 2 plus tangent x plus c.
Some integrals, however, cannot be solved as simply as the previous example. For integrals that contain a function without a commonly known antiderivative, the method of u-substitution must be carried out. U-substitution requires that the function being integrated contains all or part of its own derivative. Take the integral of sine x cosine x for one example. Here we can see that cosine x is also the derivative of sine x, and so we can assign sine x as our value of u, and cosine x as our value of du. Our integral then becomes u du. Using the power rule, our final answer comes out to be u squared over 2 plus c, or sine squared x over 2 plus c.
Let's try another one that's not quite as straightforward. So when you see an integral like this with a square root, generally what you're going to have u equal is going to be under the radical. So in this case, we have u equaling 5 plus 2x to the third. Now you know you can use u-sub for this problem because if you notice, you've got an x to the power of 3 over here and an x to the power of 2. You have part of the derivative of u. So taking the complete derivative of u, you're going to have du equals 6x squared dx. I just skipped showing out the multiplying of dx. So now you can do some substitution. So you're going to end up with the integral of the square root of u du. Now if you notice, you've got a 6 over here for your du, but your original integral does not contain a 6. So to undo this, you're going to multiply this by 1/6. So you actually want 1/6 the integral of the square root of u du. Now you can use the power rule. So you're going to want to rewrite the square root of u as u to the 1/2. So you have 1/6 the integral of u to the 1/2 du. Now using the power rule, you're going to add 1 to the exponent. So I'm just going to move over here. You're going to have 1/6 the integral, 1/6 times u to the 3/2 over 3/2, which is the same as multiplying by 2/3. So this fraction is going to be 2/18, so we're going to simplify that down to 1/9 times u to the 3/2 plus c. Don't forget your plus c. So you're going to sub back in u, and you're going to end up with 1/9 times 5 plus 2x to the third to the 3/2 plus c. And that is your answer. Here we have the integral of the cotangent of 7x dx. If you recall, there is no function whose derivative is the cotangent of 7x. So we can solve this problem by doing a quick substitution. As you know, cotangent is equivalent to cosine over sine. So you can rewrite this integral as the integral of cosine 7x over sine 7x dx. And now we can use u-substitution. You're going to want to have u equal sine 7x because you have its derivative in the numerator. So u is going to equal the sine of 7x. So now let's take its derivative. So we're going to have du equals 7 cosine 7x. Before, when we had in the previous problem, there was a 6 being multiplied, and again, you're going to want to get rid of this. So you're going to bring 1/7 to the outside. So you're going to end up with 1/7 the integral. Let's make our substitution of du over u. As you recall, du over u is the derivative of the ln of the absolute value of x. So whenever you see du over u, that's a clue that your answer is going to contain an ln. So now we can rewrite this as 1/7 the ln of the absolute value of u plus c. Now sub back in u, which was the sine of 7x, and you get the final answer of 1/7 the ln of the sine of 7x, that's absolute value, plus c. So here we have the definite integral 5 sine to the 3/2 x cosine x dx being evaluated from 0 to pi over 2. Whenever you have an integral containing a trig function being raised to a power, that's a clue that you're going to want to use u-substitution. So you're going to want to have u equal the trig function being raised to the power. In this example, that is sine x. So when you take the derivative of u with respect to x, you're going to get du equals cosine x dx. So let's return to our integral and make some substitutions. First, the whole function is being multiplied by a 5, so if you remember your integral rules, you can take out that constant. So you're going to have 5 times the integral of 0 to pi over 2, and let's make our substitutions now. We said that u was equal to sine x, so we have u to the 3/2 du. Now we can solve this using the power rule. When you add 1 to the exponent 3/2, that becomes 5/2. So you're going to have 5 times u to the 5/2 over 5/2, which is the same as multiplying by 2/5. So let's simplify this fraction. That becomes 10 over 5, which is 2. So you end up with 2 times u to the 5/2. Substituting u back in, we end up with 2 times sine to the 5/2 x. And now we want to evaluate our definite integral. So we are evaluating it from 0 to pi over 2. Now this is just like evaluating any other definite integral. So you're going to plug in these values for x in your function. So that gives us 2 sine to the 5/2 of pi over 2, which when you evaluate it is going to be equal to 2, minus 2 times the sine 5/2 of 0, which is going to be 0 when you evaluate it. So 2 minus 0 is 2. So that is the answer to this definite integral. You can also solve problems like this in a different way. Sometimes it's convenient to substitute your bounds. So once you reach the point where you have this expression right here, 2u to the 5/2, you can evaluate u at your current bounds. So if we're doing that, that's going to be sine of pi over 2, which is equivalent to 1, and then at the other bound, at the lower bound, it's going to be sine of 0, which is equal to 0. You can now write this as 2 times u to the 5/2 being evaluated from 0 to 1. Evaluating, we have 2 times 1 to the 5/2, which is equivalent to 2, minus 2 times 0 to the 5/2, which is equivalent to 0. Again, we have 2 minus 0, which equals 2. As you can see, both of these methods allow you to arrive at the same answer. Whether or not you want to substitute the bounds is a matter of the actual problem at hand and personal preference. Though keep in mind that sometimes on the AP test, especially for multiple choice questions, they will show you an answer with the bounds substituted. So always look for that when taking the test.
To summarize, in this video we have covered what the common functions and their antiderivatives are, how to solve for indefinite integrals, and how to solve for definite and indefinite integrals using the method of u-substitution. As a final tip, Always remember that it is important to memorize the common antiderivatives, and when facing u-substitution problems on the AP exam, always pay attention to whether or not you need to substitute your bounds. Thanks for watching, and best of luck on your AP exam.